Practical Science. I'm Mr. Mason, and today we're going to be investigating springs and elastic. What I've got for us today is an experiment where we're going to investigate how far a spring and a piece of elastic stretches when masses are added to them. You will then plot these results on a graph to compare the results. So you'll compare between the spring and the elastic. Before we get into the experiment, I've got my setup over here. I'm going to go through the safety steps, the steps I've taken to make sure that our experiment is as safe as it can be. Firstly, I'm going to wear eye protection. Now, this isn't because anything I'm doing here is significantly dangerous or hazardous, but this is because actually, if anything were to snap, it would then become dangerous. Okay, these are usual household objects: an elastic band, a piece of elastic, and a spring. Usual household objects, but because we are putting them under tension in a way we might not do in the classroom, at home, sorry, they could then be a hazard. The other part of it is we're working at eye level. So I've got my spring here already on this apparatus. And because that is close to my eye level, if the spring were to snap, I don't want that to end up in my eye. So while I'm doing the experiment, I'm going to wear my safety goggles. The second safety procedure is I'm going to ensure that the elastic or spring, whatever I'm testing from this hanger, is tightened securely. So this is because if it were to slip off or anything like that, we could end up with some quite significant amounts of mass being suspended. So we don't want to end up in a position where that is falling off anywhere. We want to make sure we arrange the boss of our clamp over the metal base. So this is the clamp. This is the metal base on my clamp stand. And so by suspending the mass over the base in this fashion, it means that if it were to try and topple, it would try and topple this way. So you'd have to put a lot more force here to get it to topple. And to be honest, because if I was to just slide it back slightly further, we could almost describe it as being untoppleable, because all of the mass that I'm going to pop here is inside of this pivot point, inside of the base. So now it's going to be incredibly difficult for me to topple it. It's far more likely to break the joint here than it is to actually topple over. I'm not going to overload my elastic or spring at any time. So there's a point called the elastic limit of our spring in particular, which if I were to go past that point, the spring wouldn't return to its normal shape. So I'm going to make sure I do not overload it so that I don't stretch the spring beyond its limit. The other part of this is that once you go past the elastic limit, you're then likely to snap the spring. Okay, so our equipment. I've already been through a few bits of equipment with you. But just to reiterate, so this is our clamp stand, this device here. We've got the base, and we've got the arm coming up to support everything I'm hanging from it. We've got a ruler suspended behind the spring. I'll explain why that's there later. We've got our elastic tied with a loop at each end. So here's my elastic. I'm probably going to test this elastic rather than the elastic band today. I'm only going to do two tests just to make it a bit simple. I've got my spring, you've seen that already. Now I've got a 1 Newton weights and a hanger. So these are my 1 Newton weights. They they have a mass of 100 grams. When we convert our mass into weight, into a force, we multiply, first put it into kilograms, so 100 grams written in kilograms is 0.1 kilograms. We then multiply that by 10 to get the weight of it in newtons. So 0.1 times 10 is 1. So each of these 100 grams masses is 1 newton of weight. We also have this one, which is a slight variation. This is together, this hanger and this mass have a mass of 100 grams. They weigh 1 newton. So this is so that I can support, I can put it on to start with, like this, and then I can hang additional mass onto it, like this. Okay. Talked about the eye protection already, and finally, they recommend using a G-clamp. You probably use one of these in engineering or science technology, something like that. This is our G-clamp. I'm not using this today because of the safety precautions I've taken regarding the base already. So I don't need to do this because I'm not using any masses which are likely to cause this to topple. If we were in a classroom environment though, if there were other students, if there were many groups moving around, if we weren't under the current COVID restrictions, I would insist on everyone using the clamp stand. Why is this? Well, because when people are moving around, they are more likely to bang into the table. And what we will see is that a bang into the table, it can topple quite easily either of these ways. Okay? So because we're in a very controlled environment, I'm not using the clamp stand today, but if we had other students in the room, we might be tempted to do that. Okay, so that's our safety and our equipment. So the first step you're going to do now on your practical sheet is you're going to answer these two questions in order to make a prediction. Now, a prediction is really important in science because a prediction, pardon me, a prediction is you saying what you think will happen. Now, this is how science works. If we don't make predictions, then we're not really testing what we think to be true. We're just kind of going out and observing. And that's a part of science. That's where our theories come from. But once we've got an initial theory, we then make a prediction in order to test this to see if our theory is correct. So it's really important we make our predictions so that you can see if your understanding is correct. So please would you pause the video, take about 2 to 4 minutes and answer these two questions to make a prediction about the experiment I'm about to do. If you are struggling to kind of make a prediction, if you're not sure what you're actually testing, go back to the top of the worksheet, look at the learning aims again, look at the context. If you're still struggling to make a prediction, you could then look at the method and see, okay, this is what we're going to do, and then try and make a prediction about the results. But I do encourage you to not do any Googling, to not do any kind of looking around and not jumping ahead to kind of find other people's results. Do try and make a prediction from your own hypothesis here. It's really important. Okay, let's have a go at doing the experiment then. Let's look at the method. So this is my method. Before we go any further, I'm also gonna show you the results section. So I'm going to read through the method, but I'm going to keep the results section on the board because the idea here is that you're going to fill this in while I do the experiment. Okay, so the results section is still on the board. You can see we're going to fill this table in. This is the table. The first one is for the spring. No, this is for the elastic. So we're going to do the elastic first. So I'm reading through the method on my screen here. You can be following along on your practical sheet. So on the central larger loop of the elastic, draw 2 horizontal lines 10 centimeters apart. Okay, so I've got my elastic here. Sorry, starting with the elastic, aren't we? So I've got my elastic and I've got what I'm going to do actually is I'm not going to do the method exactly as it says here. What I'm going to do instead is I only have my lines 2 centimeters apart. Now this does make my experiment less accurate. It's going to have a higher uncertainty to it. Sorry, that makes it less precise, not less accurate. So it's going to have a larger uncertainty because I'm to draw my lines closer together. So I'm just going to take my ruler off of here. I'm going to come over to the visualizer here so you can see what I'm doing. So I've got my elastic, and I'm going to do one mark here at 3 centimeters and one mark here at 5. So now these two marks are 2 centimeters apart. Okay. So it's really important we remember they're 2 centimeters apart, because when we come to do our experiment, we're going to be measuring how that distance changes. That's how we're going to measure our extension. If I can get that back on, that would be great. Okay, let's get our ruler back. And we'll slide that in there. Okay. So, step 2, hang the elastic on the clamp stand from the top of the loop. So, hang it on the clamp stand, hang the 1 Newton hanger from the bottom. So, I've got 2 on here at the moment, so I need to take 1 off. Got just 1 now. And I'm going to hang that on the bottom loop like this. Measure the distance between the 2 marks in the elastic carefully. Write this in the results table. Now I'm looking at this and I've set my equipment up in this fashion and this is how it's done on the practical sheet and I can see that. But because I've done these marks on the elastic, I think actually a better experiment design would be if I remove the ruler and then I can measure them directly. I could hold the ruler up to them rather than holding the ruler in the background. So I'm just going to lower this down. I'm going to take this off. And this is where the creativity of science comes in. A lot of people think science is just facts, but actually science is so much more than that. You need to be incredibly creative to be able to see a accurate, precise way of doing an experiment. So I'm going to measure the gap now between my 2 dots. Remember, it was 2 centimeters before. Now see it's about, sorry, it looks like it's 2.3 now, 2.3 centimeters. So I'm going to come over to my results table, I'm going to fill this in. So the distance between the marks was, 0 weight was 2 centimeters, and with 1 Newton on it, it became 2.3. Now, if you've watched Dr. Maniscalco's practical, you should have done in the last New Earth Science practical video in this sequence. She said something really important that when presenting our results, how we can be consistent about it. Pause the video, see if you can remember what I can change about my results here to make it look more helpful. Okay. If you've gone back and looked at that video, even better, well done. If you've remembered it, what it was that we need to have the same number of significant figures after the decimal point in each of our results. This shows the precision of our instruments. Okay, so I've got a distance of 2 centimeters before and distance of 2.3. Now, this was our unextended length, so immediately I can write 0.0 centimeters extension, because that was with no weight on it. With 1 Newton of weight, this is going to become 0.3. I'm working out what has changed, how much longer is it than before. Okay, so now we're going to repeat this. Step 5, add a 1 Newton weight to the hanger and measure the distance between the marks again. Write this in the table. So I'm going to add this in. So now I'm going to hold it up. Actually, I think it's easier from this side position. You can see you might be able to see I'm winking. I'm using one eye here because I want to get my precision as good as it can be. Okay, so we're up to about 3 centimeters now. Not about 3 centimeters from the precision I've got on my instrument, it was 3 centimeters. So my extension, pause the video now, see if you can calculate the extension for me. Okay, if you said 1 centimeter for the extension, correct, well done. It's gone from being 2 with no weight to 3 with some weight, so we've got 1 centimeter of extension. Okay, I'm going to carry on now with this experiment. When I come back, I will have finished these results for the elastic, and then we'll come back together and do the results. Okay, I've finished collecting my results for the elastic now. I just need to finish calculating my extensions. So please pause the video at this point, and can you fill in the distance between the marks into your table and then calculate the extension for each result, please. Okay, hopefully you've had a go at that now. So filling in the extensions, we would have 1.5, I'm subtracting 2 each time, remember. 1.9, 2.5, and 2.8. Okay. These are my results for the elastic. I'm now going to repeat my results for the spring, and I'll put these on the board for you. Okay, I've finished my experiments with the spring now. So you can see it's dangling here, and just visually you can see it's much more extended than the elastic ever was. When I had this kind of mass, let me show you on the elastic. I think I'd taken it off when I brought you back before. When I had this on the elastic, it was really only that long. It didn't get very long at all. So the spring much more stretchy, and we can see that in the kind of numbers we're getting. Although it was 2.8 centimeters to start with, it got all the way to 28.4 by the end. So what I'd like you to do is pause the video and take 2 minutes to please calculate the extension for each of these. Okay, now you've unpaused the video. Hopefully you've got similar extensions to what I did, or the same extensions as what I did. Remember, you're just subtracting the unstretched length of the material from each of your extended lengths. Okay, that's the end of our experiment now. We have our data. We're now going to plot the results so we can compare between the elastic and the spring. So your teacher will attach some graph paper to the assignment. If you can download this and then print it out, that would be ideal. If you can't do that, then any kind of squared paper would do at home. If you haven't got squared paper, then I suggest you use a program like Excel to plot your data. This isn't ideal though, because we're going to want to do a line of best fit, and Excel doesn't naturally want to do that. It naturally wants to do dot-to-dot lines. So you just need to bear in mind that if you use Excel to plot your results, we don't want to see lines going from point to point. We want to see a lovely straight line of best fit through your data. This was an investigation into springs and elastic. I'm Mr. Mason. See you next time for the next NUAS Science.